Hi and welcome. In this lecture, we are going to discuss the sample statistics and estimators. Recall that we draw a random sample of size n from an underlying population and collect data on a characteristic or characteristics of the sample. And then this sample can be considered, as we have discussed earlier, as a sequence of random variable, namely x1, x2, x3 up to xn. If we are collecting data on the age of the population, x1 would be the age of the first person in our sample, x2 would be the age of the second person in our sample, and so on and so forth. Having the sample data, we can define the sample statistic as a function of the sample that we have. Namely, a sample statistics is a function of the sample data. For example, if we consider the sample mean is the sum of the sample elements divided by n. And as you can see here, this sample mean is a function of the sample elements or sample data. In this regard, an estimator is a statistic that intends to approximate an unknown population parameter. Remember that in our context, the population parameter, for example, the population mean or the population standard deviation and so on and so forth, are not given and they are in fact unknown. If we have data from all population members, then we would be able to calculate it. Since we don't have data from the entirety of population, therefore the population parameters are unknown, and what we are trying to do using sample data is to find an approximate value or estimate them using sample data. Generally, an estimator is denoted by beta hat, which approximate a corresponding population parameter beta. For example, if we have a normally distributed sample x1, x2, xn, such that each of them has a normal distribution with mean mu and standard deviation of sigma, then a natural estimator for population parameter is the sample mean. That is mu bar, which is equal to 1 over n, sum of xi's. When we are talking about estimator, there are a couple of properties that are important for us. The first property is unbiasedness. We say that an estimator beta hat is an unbiased estimator of the population parameter beta if the expected value of beta hat is equal to beta. That means in the distribution, the center of the distribution is coinciding with the unknown population parameter. Remember that expectation is nothing but the mean, and the mean is nothing but the center of the distribution. For example, we can show that x bar is an unbiased estimator of the population mean, mu. Another property of an estimator which is important is the property of consistency. We say that beta hat is consistent estimator of beta if beta hat converges to beta in probability. That means as n gets larger and larger, remember that n is the sample size, the distribution of beta hat shrinks around beta. We can also show that x bar is actually a consistent estimator of the population mean mu. Another property of estimator which is important is efficiency. If we have an estimator beta hat, let's call it beta hat 1, then we say that beta hat 1 is efficient if the variance of beta 1 hat is smaller than the variance of any other estimator that we have for beta. Remember that all of these estimators are unbiased, but the variance of beta 100 is the smallest. The idea here is that an efficient estimator uses data in a more efficient way.